Okay, donkeys, this is a review for the AP exam, and so we are going to fly. And this is our kinetics review. So let us talk about rate. What is a rate? Well, that's going to be what? Change in concentration of something over change in time. And that rate depends upon, there could be several rates within a reaction. It all depends on the context, you might say. So if we have 2HI going to H2 plus I2, I can look at this rate of change, this rate of reaction in terms of HI, in terms of H2, or in terms of I2. So I could say, what's the rate of change? I can say, hey, the rate of change of my HI over change in time, so it's a delta over delta time, and I could express my rate that way. Or I can express my rate in terms of change in concentration of H2 over change of time, or the concentration of I2 over change in time, right? And all of those would represent a rate. Now, rate is related to stoichiometry, right? If it's a product, my rate is going to be negative. If it's a reactant, it's going to be, if it's a reactant, it's going to be negative. If it's a product, it's going to be positive. Good. And it's also related to our coefficients. And the way we do this is we take our coefficient and put that in the denominator. Good. So that's the way we would relate rate. So a negative 1/2, my rate, and this is my rate. This is another way I could write this is negative 1/2 rate of my HI is equal to the rate of my H2, which is equal to the rate of my I2, right? Good. So that is the way that we relate rates through stoichiometry. Got it? And then we might say the overall rate of the reaction would be based on a 1 coefficient. So you might say, hey, my rate of the overall reaction would be one of these two, okay? Because it's a 1-to-1. Now, it all depends on how they ask. They could say, what is the rate in terms of hydrogen iodide? Good. Factors affecting rate, right? This is old honors chem. Surface area. As my surface area increases, rate increases, right? Because there are more sites for collision. As my temperature increases, my rate increases, right? Because I have more collisions. If I have what? Increased concentration, then what's going to happen? My rate is going to increase. For why? More reactants that are able to collide. And finally, if I add a catalyst, my rate increases. And how does a catalyst affect things? Well, it lowers, remember, here's my activation energy up here. This is my activated complex. Good. So if I add a catalyst, then what happens? My beginning point stays the same, my ending point stays the same, but I have a lower activated complex, and so this would be my new activation energy. Remember, activation energy goes from where you start to the top. All right? Cool. Rate law. Now, when I have a rate law, it takes some kind of form like rate is equal to K concentration of A to the half concentration of B to the second. Good. That's the general form. And how do we get these rate laws? Hey, most of the time these have to come from experiment. And only when we can't do experiments do we come up with another way. They are not based on stoichiometry unless they are theoretical. So when they ask you, hey, if they give you data and say, what's the rate? Don't depend on stoichiometry. You have to analyze the data. Now, what's the rate order? The rate order is the overall rate order is the sum of the exponents. So my overall rate order would be the sum of those, so it's a 2.5 overall rate. But I could say, what's the rate in terms of, what's the rate order in terms of A? And then we'd say, hey, it's the coefficient, not the coefficient, the exponent. Got it? Rate constant. Okay, rate constant is my K, right? And what the question usually is what are the units on that rate constant? Now, here's the way you do that. Rate is going to be in terms of some molarity per time. Let's say it's molarity per second. Rate is always molarity per second or molarity per minute or molarity per hour. And then that's equal to K. And then in this case, we plug in these guys, right? So it's molarity to what? Molarity to the 1/2. What is it here? It is molarity to the second. Now let's do dimensional analysis. So I have what? M over S is equal to K times, what is this? M to the 2.5. Good, so what do I have to do? Divide both sides by M to the 2.5. So I have M over S over M to the 2.5 equals K. So this is really M to the 1, right? So yoink, yoink, and they ended up with 1.5. So K is equal to 1 over seconds M to the 1.5. So many times you'd see it written this way, right? And that rate, the units on that rate are going to vary based upon the rate law. All right, good. Moving on. Now we said rate laws, there are two ways to get them, either experimental or theoretical. In the experimental way, there are two ways. One is the initial rate method, and with the initial rate method, we're given what? We are given initial rates. Let's see if I have any initial rates. I don't have any initial rates off the top of my head. Let me pause and I'll come back and get some. Okay, I'm back. So let's take, if we have initial rates, we'll have something that looks like this. So we have something like NO and concentration of H2, and then I'll have an initial rate. Initial rate. That's kind of what I'm going to see. And in this case, we have 0.10, 0.10, 0.20, 0.10, 0.20, 0.10, and we have 1.3 times 10 to the minus third, 2.46 times 10 to the minus third, and 4.92 times 10 to the minus third, right? And these are experiments. Experiment 1, 2, experiment 1, 2, and 3. And so that's the general look of it. And so what do we want to do? We want to take the process is to find two experiments in which one thing is held constant. Got it? And then we're going to analyze the stuff that is not held constant. And so what we're going to do is we're going to say, hey, my rate in experiment, and I always like to have the bigger number over the smaller number. So I'm going to say the rate of experiment 2 over the rate of experiment 1 is equal to, and then we're going to take the concentration, we have to be consistent, concentration of H2 in experiment 2 to the N over the concentration of H2 in experiment 1 to the N. Got it? So then I would plug in these numbers. So I'm going to say, hey, I've got 2.46 times 10 to the minus third over 1.23 times 10 to the minus third is equal to, let's be consistent, 0.20 to the N over 0.10 to the N. And we solve for N. And so when I do that, I get 2 is equal to 2 to the N, and so N is equal to 1. So that is now the coefficient in my rate law for my H. We'll do the same thing now. We hope that we can find two H's that are constant, and so then we'll analyze those two experiments in terms of NO. So I'm going to take the rate of 3, so I'm going to take rate 3 over rate 1 is equal to concentration of NO reaction 3 to the M over concentration NO reaction 1 to the M. And so when I do that, what do I get? I get 4.92 times 10 to the minus 3 over yoink, 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 1.23 times 10 to the minus 3. Oh my goodness, I'm going to need a calculator. And what do I get? I get 4.92 divided by 1.23, and I get, this is equal to 4, and that's equal to concentration of 0.20 to the M over 0.999 0.10 to the m, which is equal to 2 to the m. So m has to be equal to what? Yoink, yoink, m is equal to 2. So that is going to go onto my right up here, right? So then when I write my rate law, that means this has a 2 on it, this has a 1 on it. So my rate law would be rate is equal to K concentration NO to the second concentration of H2 to the first, right? Good. And then from this, I could calculate the units on my K. Now, how can I get my K? If I wanted to get my K, then I could take any of these experiments, such as experiment 3, and drop it into our rate law. Got it? So I'd take my 0.2 and put it in here. I'd take my 0.1 and put it in here. Put my 4.92 and put it up here, and then I can calculate my K. Any questions on that? All right, good. It can get more confusing, and if so, remember the really what we're doing is we are saying rate 2 equals K. My K doesn't change as long as my temperature is constant. Concentration of H2 in the second experiment, concentration of NO to the second experiment, M and N, right? And then we're going to set up a ratio for whatever rates. And that you may have to do this if they give you 3 different variables. Okay, that should be an M. Okay, good. Any questions on that? All right, moving on. What happens if I have, oh, that's the integrated method. Integrated method, how do I recognize the integrated method? In the integrated method, what I have is time versus a concentration. Okay, and this is a graphical method. And we are only going to assume there's 3 options. Either I have 0 order, first order, or second order. Good. So now, what do I graph to figure these? Okay, let me back up. If I graph these, I should be able to get a straight line. My right answer will give me a straight line. If it's 0 first or second, if the 0 order gives me a straight line, then that is it. If it's first order that produces a straight line, then it's first order and so forth. So what is my straight line? If I have concentration versus time, if that gives me a straight line, then it is 0 order. And what is the equation for that? Concentration at any time is equal to negative KT plus concentration originally. Okay, so that is the equation of the line that will, if it's 0 order, first order, we go with logs, right? Natural log of concentration versus time. And the equation for the line is natural log of the concentration at any time is equal to negative KT plus the natural log at time 0, right? By the way, y equals mx plus b. So that means what? That means my k, my slope, excuse me, in this case, my slope is negative k. So I look at the graph and find the slope and take the negative of that, and that's my k. Here, once again, my m is equal to the negative k, but I'm graphing a different thing than I did up above. And finally, if it's second order, it's 1 over concentration versus time. And so I'd graph 1 over concentration at any time is equal to KT plus 1 over concentration initially. And in this case, my slope equals my K. I'm going to ignore that phone call. Good. Now, for all of these, there's also half-lives that we can produce, or there's an equation for the half-life. And let me write those down for you quickly here. Okay, Half-life for zero order. Concentration, half-life for zero order. Concentration over 2K. That's my half-life. First order, 0.69. 0.69 over K. And the last one, it is 1 over the concentration, the initial concentration of K. Notice here, for first order, it is completely independent of concentration. That's important. If you look at that, if you look at data and the half-life doesn't, if the half-life is consistent regardless of the initial concentrations, then it's got to be first order. Okay? All right. Good. Moving on. Activation energy. Okay, we drew a picture of we drew a picture of activation energy, right? We've got this thing here, and this is energy, and this is extent of reaction, and we draw something like that. And if this is higher and this is lower, that means my products have less energy than my reactants, right? Less energy, so that's delta H is a less than 0. That means this is exothermic, right? And the distance from where we start, always from where we start to the top, is my activation energy, right? Now, if I go in the reverse order, shoot, let me get that. Okay, so sorry about that disturbance. Let us talk real briefly about how we can get activation energies. And there's a graphical method, and what are we going to do? You're going to graph the Arrhenius equation, and that means you're going to take, you're going to need, for these, you're going to probably need Ks and temperatures. You need different Ks at different temperatures. So you can take the log of K and graph it versus 1 over the temperature. And of course, these temperatures have to be in absolute temperatures. And when you do that, your slope, the slope of this line, is going to be equal to negative EA over R, where R is 8.314 joules per mole Kelvin. And so the negative slope, so we can get the EA from that. That is the graphical method. And what we're looking for here is they'll give you Ks and they'll give you temperatures and they'll give you a bunch of these. And so you have to graph that and then you can get the slope. Good. The non-graphical method is if you have at least 2 data points. That means you want 2 different Ks at 2 temps. And how are we going to find the EA? We're going to say that the natural log of K1 over K2 is equal to EA over R, EA, that's my activation energy, over R, times 1 over T2 minus 1 over T1. And once again, this is 8.314, and these temps are in Kelvin. Got it? All right. So that kind of does it here. Very quickly, determining rate loss theoretically. Okay, remember I said there's 2 ways we can determine rate loss, either experimentally or theoretically. And if you don't have any data, we're going to try to figure them out based upon molecularity, right? Molecularity. And that means, hey, if I have just A going to something that's unimolecular, if I have A plus B, that is bimolecular, right? And then A plus B plus C or A plus 2B, these things are trimolecular. Rare, this does not happen. That means these all have to happen simultaneously. That means B must collide simultaneously with A. Okay, that could make sense. So you can't get bimolecular, but do you really get an A and 2Bs all colliding at the same time? No, that is not rare. So we're going to use this knowledge and we're going to base our rate off of that. And so Usually they're going to give us steps, and so they'll give us steps, and they're going to tell us the speed or the slow step. And when the first step is slow, that's easy. How do we write it? We just let's say the first step is a plus 2b. Okay? Going to blah blah blah. If that's the case, we're going to just base the rate on the coefficients. And we're going to say that the rate is equal to K, concentration of A, times concentration of B squared. That is if this is the first step. And we ignore any other step as long as my first step is slow. However, if my second or third step is slow, then we have to do something else. So let us consider 2NO plus BR2, and that is going to NOBR2, and that's fast. That means I have a fast first step. So first step is fast. Good. That means I cannot use what I just did. I have to look at the second step. Second step is NO plus NOBR2, and that yields 2 NOBR, and that is slow. All right, now we're going to start and base our rate on this. I'm going to say, hey, rate is equal to K, concentration of NO times concentration of NOBR2, right? Oh, let me show you. I really need to tell you what the overall reaction is. The overall reaction is 2NO plus BR2. Oops. Excuse me. This is my over. Yeah. What? What? Here we go. BR2. Sorry about that. We're going to make the class stand out in the hallway for a few minutes. It's third hour, and no one really likes that class, right? Okay, so here's my overall reaction. Oh, some of you are listening to that. Sorry, I apologize. Only those of you in third and fourth hour who are not listening to this those are the only ones I don't like. Everyone else I do like. If you're listening to this, of course I like you. Good. So this is my overall reaction. So when I look at this overall reaction, I look in here and I see I have a problem because this doesn't tend to show up. Now, that doesn't always happen, but the indication is I need to replace this. And how am I going to replace it? Well, I'm going to go back to my fast, and I'm going to assume that it's an equilibrium. Got it? So that means I have two reactions going on. I have an NO plus, I have 2NO plus BR2. This is my forward reaction, and that leads to NOBR2, right? But then I also have a reverse reaction, which is NOBR2 yielding 2NO, and that's the reverse. We'll put an R there, plus BR2. Got it? And now I'm going to write both of these I'm going to write the rates based upon the coefficients. So for this one, I'm going to say the rate, and we'll call that forward, is equal to Kf times concentration of NO squared times concentration of Br2, right? And then I can have the rate of the reverse right here, which is equal to what? Concentration of NOBr2, right? Since it's at equilibrium, what do we know about the rates? That means they are equal. So that would mean that I have Kr times NOBr2, right? Good. So having done that, I am going to solve for what I want to replace here. Got it? So I'm going to say that concentration of NOBr2 is equal to Kf over Kr, concentration of NO2 over concentration of Br2. Got it? And then I'm going to substitute that in right up there. So my total rate is going to say that the rate is equal to K times what? Times Kf over Kr times NO2, NO squared, times Br2 times this NO, right? Times NO. Got it? So all this becomes one big K. So K times concentration of NO, well, how many NOs do I have? Cubed concentration of Br. There we go. So that is how we figure that out. I hope I did that right. Somewhere around there, somewhere I have a mistake. Shoot. Oh, right here. There shouldn't have been a 2 there. Sorry about that. So there's no 2 there. So there's no 2 there. So there's no 2 there. And so that makes that a 2. There we go. So that's how you do it. Okay, folks, that's it. That's a quick. If you weren't here, then that's the review. Got it?